Good evening, everyone. My name is Renu Raman Sahu, and today we will be discussing about the introduction of the quantum mechanics and how it applies to the Drude-Lorentz model, and what are the corrections we have or we can incorporate when we consider the quantum nature of the electrons. So, and then we will discuss some of the previous year questions. So about the history of quantum mechanics, it has been a very uh, it has been a subject which has tested which has been time tested, and it has been quite successful. So during the end of during 1900s, it was such a time where people used to think that the science has science is already a complete subject and there is no more development to be done, and there are some incremental work that needs to be done and to find some values of constant and to fill some of the gaps, but the fundamental science they were thinking that it was complete. But there were some experiments like this black body radiation, and uh, these are some of the experimental results which couldn't be explained by the classical physics, like black body radiation and the discrete nature of the atomic and molecular spectra, and the Compton effect, which is an inelastic scattering, and photoelectric effect. These were some of the phenomena which were uh, not been able to explain by the classical physics. Okay, so today will be and that actually set the ground for a whole new subject of quantum mechanics, and it has now so we now understand quantum mechanics uh, very nicely, and it has formed mathematical footing. So in 1959, let us start with the discussion of the first example, the black body radiation. So what it means is the every body radiates some energy by virtue of it being in certain temperature T. That is called black body radiation. When a body is in thermal equilibrium, it will uh, emit some energy. One of the perfect example of a black body, like which absorbs everything, which whatever falls on it, is the graphite surface. And Kirchhoff had designed a black body in 1859, and uh, which is like this. And the so there is a small opening here, and here is a mirror, a pointed mirror. So whatever falls on it, it gets and it whatever the light will fall on this part, it will get reflected back, and it, it will have a very less probability less probability to escape this body. So this is the design of the black body, and when you keep it in some other in a dark room, let's say, then this trapped energy they can come out by from this hole. So this is the property of a black body. So there are two known properties. So as we increase the temperature T of the body, the intensity of the radiation which is coming from the body will also increase. The intensity means the energy per unit area per unit time. And higher the temperature, lower is the wavelength at which most of intense part of the spectrum higher is the wavelength of the most intense part of the spectrum. So we'll see this in a while what it means. So in black body, so it is a curve between curve between the spectral radiance, which is watt per meter cube, which is nothing but watt per meter is the intensity, and intensity per meter or power per unit. That is the spectral radiance, and we plot the spectral radiance with respect to the wavelength, and we try to see what is at which uh, so this is the spectral radiance is this is how it is defined. Spectral radiance is r as a function of lambda at some particular temperature at some fixed temperature T, and we obtain the intensity by integrating over all the values of lambda uh, from 0 to infinity, and this r is the spectral radiance, I is the intensity. Spectral radiance, I is the intensity. which basically means that the area under this graph is the intensity. Now you see, as temperature increases from T2 to T1, so this is at higher temperature, the area under this curve is more than the area under this curve, which means that the intensity is increasing as we increase the temperature of the body. And the second point is that the wavelength at which, this is lambda 1 and this is lambda 2, the wavelength at which the intensity, the spectral radiance will peak, is less when the temperature is more. So these two graphs, these two statements about the intensity and about the maximum lambda, that are experimentally observed and captured in these two laws. One is the Stefan-Boltzmann law, which tells you about the intensity. So the intensity, how do you get? The integral area under the curve, or the integral over the spectral radiance over all wavelength, that goes as lambda T to the power 4. So as you increase, if you increase the temperature by twice, then the intensity will increase by 2 to the power 4 times, which means 16 times. And Wien's displacement law, this can be captured as like this, but lambda max into temperature is a constant, or lambda max is inversely proportional to the temperature, and it is given by this formula. These are the constants. Sigma is the Stefan-Boltzmann constant, which is 5.67 into 10 to the power minus 8 watt per meter square per Kelvin 4, and this is 2898 micrometer Kelvin. So that means this temperature has to be expressed in Kelvin. So the spectral radiance, this we just discussed, that it is defined as such that this R lambda T d lambda is the power per unit area whose wavelength lies in lambda and lambda plus d lambda in this small narrow range. And this is the statement of Stefan-Boltzmann law. And where this comes from, so we want to understand from a model how so this we should, if we develop some model, or the like for example kinetic theory for the gases, so from those microscopic model we should be able to calculate R of lambda T. From classical physics, what we get is, from classical physics we get this expression. By classical physics we mean the Maxwell equations, where the waves, the light is treated as an electromagnetic wave. Light is an EM wave. When light is treated as an electromagnetic wave, we get this expression for R lambda T. If you plot this R with respect to lambda, what you get here, at very high lambda it is almost falling to 0. At very high lambda R goes to 0, and at very short lambda this goes to infinity. But what we see in reality what we see is this red curve here. That is the experimental plot. So it matches very well at high wavelength, but at low wavelength we see a very big divergence. Instead of falling, the Rayleigh-Jeans formula, it goes up, and this is the UV region because the wavelength is small. So this is also called as ultraviolet catastrophe. So to solve this, what Planck did, so Planck assumed that let's say the energy can be absorbed in steps of some particular fraction, some particular integral multiple of energy packets h nu. So when we assumed that, he got this formula of spectral radiance, and at high wavelength it matches very nicely. At high wavelength lambda will be lambda will be very very high, so hc by lambda kt will be small, and here you can expand up to terms of the order of 1 by lambda, and what you get is hc by lambda kt. So it goes as 1 by lambda. So at high wavelength it measures very well, and even at low wavelength you get a a very nice match for the Planck's expression of spectral radiance. So Planck's spectral radiance, this actually solves the ultraviolet catastrophe. So even though during those time, so this was the fact that the main input to this is that h nu, the energy can be absorbed by the oscillators only in packets of h nu or integral multiples of h nu, not as fraction of them. But there was no first principles from which this was observed. Uh, this was derived or this was inferred. So that is why Planck himself was not that much satisfied, and he like stated this as an act of despair to match with the experimental result. So that is, this is the very birth of the quantum nature of the understanding of the quantum nature of light. Then what happened? So the main uh, what was established, the fact that was established was that energy is uh, in packets of h nu. Even though the scientists were the Planck was not convinced himself, but this was a necessary step to match with this experimental result. And from fitting what he observed, he got somewhere around 6.5 into 10 to the power minus 34 joule second. That was the experimental one when Planck did the fitting, and today what we use is 6.656. This is one of the accurate value. So uh, then came the photoelectric effect, where Einstein, what he did, okay, the scientists, during those time they were not sure if what they were saying was correct or not, and there was no fundamental reason why they should do no fundamental reason in the framework of classical mechanics why they should accept the quantization. But Einstein told that, okay, let us assume that this is true. We shouldn't let us not question about the quantum nature. Just by assuming that uh, photons, the energy, light energy are in packets, he could explain the photoelectric effect. So what are the key features of photoelectric effect is that no electrons are ejected regardless of the intensity of the incident radiation, unless the frequency of the radiation nu, it will exceed a certain threshold value. Only after that the emission of electron from a particular metal will take place. And the kinetic energy of the ejected electrons, it increases with nu of the with the frequency of the incident radiation, and it is independent of the intensity of the radiation. So this is one of the important features, that it is independent of the intensity, but it depends on the kinetic energy of the electron depends on the frequency. And even at very low intensity, electrons are ejected if that threshold is exceeded. So the half mev square, so this is h nu minus the work function. So the frequency corresponding to this work function, if that is exceeded, then what we get is some kinetic energy of the electrons. And so the explanation of this photoelectric effect suggests that the electromagnetic radiation of frequency nu, it cannot have an arbitrary energy, and it can possess energies in multiples of h nu only. And the second point is that the EM radiation of frequency nu, it behaves as though it consists of like 1, 2, 3 and like an integral number of particles, with each with energy h nu. And the particle nature of light, it came to be known as photons. And before that, Newton also thought that light can be like particles called corpuscles, but his idea was abandoned because he didn't have any proof. And as interference and diffraction, which were clearly the wave nature or the wave phenomena of light, they were discovered. So people started thinking that, okay, electromagnetic wave, light is a form of electromagnetic wave, and the particle picture was abandoned till Einstein. So light can behave as a particle, and Einstein gets the credits for this because he boldly stated that, okay, let us, so whatever Planck has discovered, let us take that to be true. Then for photoelectric effect, Albert Einstein, he got the Nobel Prize in 1921. And so what this experiment did, light can be thought of as waves. So what Lee de Broglie, he suggested that, okay, since light can be thought of as a particle, so particles can also be thought of as a wave. So what he told that any particle traveling with a linear momentum p, it can be thought of as having a wavelength lambda, which is given by h by p, where h is the Planck's constant. And soon after that, Davison and Zermert, these are two uh, experimentalists, they demonstrated the beam of electron, it can undergo diffraction, and diffraction is something. So electron is a particle, and the fact that they could diffract suggests that electrons are behaving like waves. And electron from heated filament independent incident on a nickel sample, they demonstrated diffraction. uh, this they showed in 1927, and this established that wave particle duality is there. So quantum mechanics, this laid the foundation of quantum mechanics, this wave particle duality, and all the experiments happened before, the Compton effect and so on. There are all other developments that have taken place that laid the foundation of the quantum mechanics. And uh, so the formal background of quantum mechanics, so the mathematical formulation in which uh, we can infer all the properties of the quantum system from this quantity called the wave function. The wave function psi, it can be obtained by solving the Schrodinger equation, and Schrodinger equation is given by this is minus h bar square 2m del square psi plus v psi is equal to E psi, and it is an inspired equation, and it couldn't be derived from any first principles. And Erwin Schrodinger and Paul A.M. Dirac. So there is another formalism of this quantum mechanics, solving quantum mechanics, called Dirac formalism. So it is quite useful in quantum mechanical calculations. So for that, Schrodinger and Dirac, they got the Nobel Prize in 1933. And but during those times, the notion of wave function was there, but there was no physical interpretation of this. And it was Max Born who interpreted psi as the probability of finding the particle between. So psi is interpreted such that the mod square of psi is the probability density. What it means is mod psi square dx is the probability of finding the particle between x and x plus dx. So and for this, Max Born got the Nobel Prize in 1954. And there was another important scientist, Niels Bohr, who explained the discrete nature of atomic and molecular spectra in his Bohr's model, where he assumed the quantum nature of the quantum mechanical picture of the atomic particles. So what we can conclude is that the wave function psi, it can be considered as sum of more than one wave function, each having a momentum. In such a case, some measurements will indicate one value of the momentum, and other measurements will result in other values of momentum. So this principle, it is also called the superposition principle. And so what this statement says is that a particular wave function can be the sum of the momentum eigenstates. Okay, and all the momentum eigenstates, they form something called a complete set. By complete, what we mean is that given any wave function, you will be able to express it as the sum of this momentum eigenstates. And what we mean by the localizing of the particle, it means that the particle will require that the probability of finding the particle in a very small region, it should be nearly 1, and its wave function looks like this Dirac delta function. However, this like if we can measure the momentum, we have to add many momentum. If we want to find or find the particle at a very localized place, we have to add a lot many momentum states. What it means is that now the momentum will vary across a large range of values. and that has to be there to make this wave function. So theoretically there is a certain uncertainty, so we cannot measure the position and momentum simultaneously, and there is a lower limit of the accuracy, it is h by 4 pi, and it is not just the experimental uncertainty, it is the theoretical reality. And so that's what we called Heisenberg uncertainty principle, and he got the Nobel Prize in 1932. And in 1945, Wolfgang Pauli, he got the Nobel Prize for Pauli's exclusion principle. These are some of the important events or important contributions of the scientists. Planck, the summary. So let us summarize all that we have learned. So Planck's contribution is that energy can be quantized in terms of frequency, h nu, where h is a constant. De Broglie told he established this wave particle duality, that any particle of momentum p will have an associated wavelength lambda, which is h by p. So Schrodinger, he told about what the energy states or the wave functions will look like, and this wave function was this wave function psi has an interpretation of probabilistic interpretation, which was given by Max Born. And what he told was that psi mod square dx is the probability of finding an electron between x to x plus dx. And the third most and the last most important contribution is this Heisenberg, who told that one cannot determine the momentum and position simultaneously of a quantum mechanical system. Now let us try to understand how the Drude model, how quantum mechanical principles was incorporated into the Drude model. It was done by Sommerfeld, and Sommerfeld is quite famous, particularly because four of his students like Heisenberg, Debye, Wolfgang Pauli, and Hans Bethe, all these were Nobel laureates in different areas like physics, chemistry, like astrophysics, and so on. But all of them were the students of Sommerfeld, and he was the one who incorporated the quantum principles to the Drude model. So what he told was that he also assumed that the free electron picture of the electrons in a metal, but now he applied quantum mechanical principles to the Drude model. And what quantum mechanical and furthermore, by quantum principles one means that the electrons are identical, as well as they are they're not only identical, they are indistinguishable. And Pauli's exclusion principle is also applied, and what Pauli's exclusion principle is that no two particles can two electrons with same quantum numbers, they cannot occupy the same state, and the potential within a metal is constant. And the implication of this is that the electrons are identical and indistinguishable, and because of that, and since the electrons are spin-half particles, they have to obey the Fermi-Dirac statistics, and they have to obey the Pauli's exclusion principles, and particles are identical and indistinguishable. So what Drude had imposed, he imposed the laws of kinetic theory, and kinetic theory applies to classical particles. So what he basically did was applied the Maxwell-Boltzmann statistics, which the classical particles obey, to electrons, whereas electrons are fermions, and they, just because they are indistinguishable and identical, they obey and they follow the Pauli's exclusion principle. They follow something called Fermi-Dirac statistics. So one of the main differences in the Drude model and the Drude-Sommerfeld model is that the statistics are different. So why the statistics are different? In classical particles, swapping the particles, it will give a new state, whereas swapping the particles between energy states, it do not give a new state. It is the same state because the particles are indistinguishable. So the manner of counting the number of states, number of microstates, it will differ, and that is where the key important difference comes in. And second is there is a fixed number of states at each energy level. Let's say that at energy E1. So for example, in classical particles, let's say the energy states are E1, E2, E3, ER, up to here it is there, and the number of particles are N1, N2, N3 for corresponding to each energy state. And we are saying that there is no upper limit in Ni in classical particles. So all like there is no upper limit for that. Okay, no restriction on this Ni. However, in quantum particles, the number of particles which can occupy energy E1 has an upper limit S1, where S1 is the number of states in energy EI. So, and this is the consequence of Pauli's exclusion principle. So, this plays a important role in determining what is the Fermi statistics, the Fermi-Dirac statistics. So, these are all the theoretical part, and based on this, let us discuss some of the questions. So, the first question, let us see, the human body emits dash radiation. So, the fact that human body has a temperature at 37 degrees Celsius, which is 37 plus 273 Kelvin, which means 310 Kelvin, it will emit intensity according to Stephen Boltzmann law of this intensity, and it will emit. So if you find the lambda, so at this intensity, but what we want is to determine at which wavelength. Let us do this lambda max T. This is the Wien's displacement law, 2898 micrometer Kelvin. So if you do this, lambda max equal to 2898 micrometer Kelvin over T is 310 Kelvin. So what we will get out of this is 2898 divided by 310. It is around 9.3 micrometer. So this falls in the infrared region. Yeah. The classical physics fails to explain the death because of the quantum mechanical nature of the particle. Okay, so photoelectric, we saw the examples recently that the photoelectric effect, it requires the particles to be quantum. The particularly the photon, it its quantum nature was crucial to explain the photoelectric effect. So that's why Einstein got the Nobel Prize in 1921. The Compton effect, the modified quantum Compton effect, is also another experiment in which a photon h nu will hit the electron, it will scatter off, and the scattered photon, it will have h nu dash, and nu dash will have less frequency than, or the less energy than h nu, because it has given out some energy to this electron, and this is nothing but your Compton effect. So basically your lambda, it will become lambda dash corresponding to this will become more than lambda. So that is your modified quantum effect, and it can be explained if you only by the quantum mechanical picture of the photon. And the discrete spectra of atom and molecules, this is also for this Niels Bohr got the Nobel Prize to explain this by uh, uh, by using the quantum picture of the light. So it is all of the above. This is the correct answer. So match the following. So what is Planck's constant? Planck's constant is h, and it has a value of 6.626 into 10 to the power minus 34. So 1 is C. Stephen Boltzmann constant, it has a value of, so one, either you remember the value, other you can remember the unit. For example, this Stephen Boltzmann constant, it has a value of this 5.67 into 10 to the power minus 8. But in case you don't remember this value, so intensity is sigma t to the power 4. This is in watt per meter square, or watt to the power minus 2, the dimension of sigma, and this is Kelvin to the power 4. So the dimension of sigma is watt per meter square per Kelvin to the power 4. So see, this unit matches with Stephen's constant. So this is your correct answer. So 2 will be D. The speed of light is, again the unit will be meter per second, but it is a known constant, so it is 3 into 10 to the power 8 meter per second. Yeah. And the last one is the Boltzmann constant K, and it is 1.38 into 10 to the power minus 23. So this is 4B. So this combination will be your correct answer. 1C 2D. So 1C 2D is this, 3A and 4B. So this is your correct answer. What is common between Drude and Drude-Sommerfeld model? So both use the concept of free electron model. This is correct. Both models apply quantum mechanical picture. This is wrong. It is only the Drude-Sommerfeld model which applies the quantum mechanical principles. And both model incorporates Pauli's exclusion principle. This is also wrong. Only the Sommerfeld model does that. So both models assume that the potential is constant within the solid. So this is correct, because both of them assumes the potential to be constant. The Drude-Sommerfeld model and Drude model follows dash respectively, and it is given the options of different statistics. So we know that Drude-Sommerfeld model assumes the electrons to be fermions, and they will apply the Fermi-Dirac statistics. So Fermi-Dirac statistics, and the Drude model, it applies kinetic theory to the electrons, so it follows the Maxwell-Boltzmann statistics. So the correct answer is Fermi-Dirac statistics and Maxwell-Boltzmann statistics. Let us do this question. The diffraction phenomena was originally interpreted as the experimental confirmation for the particle-like behavior of a matter. So this statement is wrong. So when Newton gave the corpuscular theory, but he didn't, later people found that light exhibits interference and diffraction. These are the well known wave like nature. This can be explained by the wave like behavior. So diffraction phenomena, it is originally interpreted as not as particle but wave. So this statement is false. And light, that is why we call light as an electromagnetic wave, and that is why Maxwell's and electromagnetic waves which follows Maxwell's equations. Okay. A sample absorbs at 530 nanometer and re-radiates energy at 633 nanometer. What is the frequency of oscillators emitting the radiation? So emission is happening at 633 nanometer. So and absorption at 530 nanometer. But what we want to understand is what is the frequency of oscillators. So oscillator, so we look at the emitting part. Emission is happening when the sample will re-radiate, which is 633 nanometer. So the frequency at which it will re-radiate is mu is equal to C by lambda, and C is 3 into 10 to the power 8 meter per second, and lambda is 633 nanometer, which means into 10 to the power minus 9 meter. And if you calculate that, it turns out to be 0.47 petahertz, or 0.47 into 10 to the power 15 hertz. So religion's law. So what is religion's law? Religion's law, it says that this is r lambda t, and this is your lambda, and religion's law is like this. This is the spectral radiance of a black body. It goes as 1 by lambda to the power 4 for a given temperature. So, but what is the actual spectral radiance experimentally observed is like this. So, it is not applicable at lower wavelength. So, at lower wavelength, it is not applicable, which is true. This is true. Results in an ultraviolet catastrophe. So, it results in an ultraviolet catastrophe because at low wavelength or the UV region, what is happening is there is a huge divergence of this spectral radiance from Religion's law, from these experimental values. So this results in ultraviolet catastrophe, and it is not based on quantization of energy, which is also true. It is not based on quantization of energy, but the fact that electrons are waves, and it is not applicable at higher wavelengths. At higher wavelengths, there is a good experimental match with this Religion's law, so it is applicable at higher wavelengths. So the correct answer is only the first three. The black body radiation plot is between the spectral radiance and the wavelength of the emitted radiation at temperature T. If the black body radiation temperature of the black body radiation is decreased by 20 degrees Celsius, then the areas under the power density per unit wavelength. So power density per unit wavelength is nothing but your spectral radiance. So this R and this is lambda. This is spectral radiance. What happens to this if the area under this curve will give you the intensity, and intensity at some temperature T is given by sigma T to the power 4. Okay. So what it is saying, if the temperature of the black body radiation is decreased, if the temperature is decreased by 20 degrees Celsius, so whatever the temperature, you have to subtract it from 20, then intensity will also decrease. So areas under the curve, so areas under this you can just replace by areas under this curve, you can replace by intensity I of T. Okay, if temperature will reduce, then temperature this quantity areas under the power density curve, that will also decrease, and it will decrease because like whatever the fraction, this will decrease, that to the power 4 times it will decrease, and it will, since it is decreasing, it is changing. So these are the two correct answers. So this is the calculation of question number 2. You can go through it. So a graphite die heated at 1200 degrees Celsius for 30 minutes and then immediately kept in a location that is at room temperature. So for 30 minutes graphite is heated at 1200 degrees Celsius for 30 minutes. In that 30 minutes, thermal equilibrium would have achieved. That means graphite is now at 1200 degrees Celsius. That means it is emitting at this intensity I of T is equal to sigma T to the power 4, where temperature is this thing in Kelvin, this plus 273 Kelvin, 1200 plus 273. So where T is equal to 1473 Kelvin, you have to put it here, and whatever the intensity you guessed, it's the intensity at which that graphite is radiating energy. Now When you immediately keep it in room temperature, T equal to room temperature, immediately it will still be in 1473 Kelvin, because it will take some time to achieve the thermal equilibrium. So it will and from room, the fact that room is at temperature T, it will emit at I of T equal to sigma T4. The intensity from room to black body, this is this will be less than the value from black body to so okay, what would be the room temperature? Room temperature is 300 Kelvin, let's say. So I of T from room is sigma T 300 to the power 4. So since this value is less than this, there will be a net radiation of the energy. So it will display so first of all, it is a graphite, so it will be equivalent to a black body, and the second, it will display a net radiation of energy because the radiation emitted will be more than the radiation it will absorb. Okay, now this question, two samples A and B are at temperature 25 degrees Celsius and 100 degrees Celsius, and they are kept in a dark room. So what is the peak radiation wavelengths? So what is the formula that you should use? That is the Wien's displacement law. So lambda max T is equal to 2898 micrometer Kelvin. So if you solve for that at 25 degrees Celsius, what you get is around 9 micrometer, and at 100 degrees Celsius what you get is around 7 micrometer. So it is 9 micrometer and 7 micrometer respectively. Okay, so in quantum mechanics, counting of microstates is impacted by so electrons are indistinguishable in nature, it is correct. Electrons are identical, it is correct. Distinguishable nature of electrons, so this is false. And the need to use Fermi-Dirac statistics, we need to use this because electrons are fermions and they follow Pauli's exclusion principle, they are indistinguishable and they are identical. Protons and electrons differ from each other because the difference in, so what is the charge? In charge, a proton is a positive charge, plus 1.6 into 10 to the power minus 19 coulomb, and electron is minus 1.6 into 10 to the power minus 19 coulomb. Even though the magnitude is same, their sign is different, so it vary in charge. What is the mass of, this is proton and this is electron. Okay, in mass also they vary. The mass of electron is 9.1 into 10 to the power minus 31 kg, and mass of a proton is mass of proton is 1.67 into 10 to the power minus 27 kg. So, and about the size, so electron has a size less than 1 by 1840, that of size of proton. So in size also electron is quite less, but the spin of both of them are spin half particles. Both electron and proton are spin half. So the correct answer is charge, mass and size. Okay, so calculate the approximate intensity of a black body heated at this. So intensity, you can easily calculate by the Stephen Boltzmann law, sigma T to the power 4. Sigma is 5.67 into 10 to the power minus 8, and T is given in, so you have to remember that T you have to input in Kelvin. So T equal to 4727 degrees Celsius, which is 4727 plus 273 Kelvin, which means it is 103 plus minus 50 Kelvin. Okay, so 5123 to the power 4, which means 5.67 into 6.25 into 10 to the power 2 into 10 to the power minus 8 to 10 to the power 12, which is around 3500 into 10 to the power 4 watt per meter square. So this is your correct answer, which is this. Calculate the approximate intensity. Okay, so this is your calculation of the previous question. So match the following. What Max Planck did, Max Planck, he told about the quantization of energy. So Max Planck is quantization of energy 1c. Okay, the next is, so from here already you see there are two options, this or this. One of them might be correct. So Louis de Broglie, what he did, he told about the wave particle duality. So the wavelength is given by h over p. It is the wave particle duality. So this thing 2 is E. So 2E, 2E, both are 2E. Okay, now let us see Erwin Schrödinger. Erwin Schrödinger, he gave us the Schrödinger equation. Schrödinger equation is, or the wave equation. Schrödinger equation is the wave equation. So 3A. Then what Max Born did, Max Born is, this is wave equation. Wave equation is nothing but minus h bar square over 2m del 2m del square psi plus v psi equals e psi. Erwin Schrödinger and then Max Born. Max Born, he interpreted that psi mod square dx is the probability of the, he interpreted the wave function as this, that this is the probability. So this is the contribution of Max Born. So 4f, and so 3a and 4f is already here. He is saying 4b, it is wrong. So what did Werner Heisenberg did? Werner Heisenberg told about the uncertainty principle. Heisenberg's uncertainty principle, that's how it is known. So 5b is here, and 6 is Albert Einstein photoelectric effect, and photoelectric effect says that light can be treated as a particle. So it is 6d. So this is your correct option. This is wrong. So thank you so much for joining. We'll meet in the next week.